Okay. That is not correct. Let's do this. What? It's not really 4 slides. So generally speaking, we're going to be moving away from using slides at all. You will see here, today in Astronomy 4000, we'll talk about CCDs. What are they? How do you convert into digital numbers? Now, some of you may be saying to yourself, well, I really want to do a physics project. So perhaps none of this will matter to you. You are welcome to, once we finish talking about the scientific writing component, if you're like, I'm dead set on never doing an ASTR project and I have a great idea lined up and I'm going to do it, then fine, go ahead, you can leave, right? There's no restrictions on whether or not you need to learn about CCDs. But in order to be able to do the data manipulation part of this class, if you plan on doing even a small section, you have a question? Okay.
Yeah.
So we have this book, right? This is in your what is it called? In the syllabus. So in the syllabus has Handbook of CCD Astronomy, and I have the sections that are lined up in here. So we'll talk about what is a telescope, how telescope work, how CCD make picture, right? CCD make picture like this, right?
Yeah. Was the CCD the thing that sees like the light, I guess?
We'll talk about that.
Okay.
Yeah. Okay, so we'll talk about the technical aspects of all of the work that we'll do. Then we'll talk later on in the semester. So every other week, we're going to be going basically between scientific writing and detail. And at the beginning of every class, we'll discuss how to improve your writing and the things that I'm expecting of you. And then what you're going to be doing later on throughout the semester. Then every other week, we'll talk about the technicalities of the types of data analysis you're doing. So there'll be certain weeks that you'll want to come, even if you're not working on CCD data. So when we're talking about how we understand statistics, how we understand error and error propagation, those are ones that you'll want to pay attention to. Because regardless of how you take the data, you have to understand what the inherent uncertainties are. Questions? Okay, so I just handed you back some summaries. And just to sort of go over them with you. So the first thing that you'll note is that, oh yeah, okay, so a lot of people took it to heart already. Why do I like this?
You'll understand it. Right.
Good. Yeah, so handwritten is fine, right? First time, I'm not going to introduce too many rules to you at the same time, because then you're just overwhelmed. But the first goal is to summarize the work, right? And so you summarize the work and you put it on paper. And then I edit it and I hand it right back to you. So if you hand wrote it, now you have to handwrite it again, which kind of sucks for you. So even though it may seem like extra work, putting it in this format is better, right? Because then you just go and you type it and it's better. What else do I like about this? Yeah, what is the difference between this and what is the difference? No offense. Between this and this. Ah, there's space in between. So why is that helpful for me as an editor? No, I'm never going to write a nasty comment, but instead of just writing maybe a question mark, I might be able to be more specific about why the choice that you made in that particular sentence is either good or bad, or I have a question about it, right? So I can give better feedback when I have more space in between to write that feedback, right? Other benefit to using this? Spell check, grammar, look for those squiggly red lines. That's really helpful, okay? That's what I do, right? I don't actually, I just type, and then I look back and I go, oh, this is all filled with spelling errors, right? Okay. Oh, sorry, folks. Jose, this is for you. Yeah, I guess I should have put a sign in there. They kicked us out of that other one. What? But outrageous, right? Outrageous. Okay. So I was just summarizing that when you're turning these in right now. They should be printed. I like them printed. I'm not going to ever give you points off for handwriting, right? This is beautiful handwriting, by the way. So as long as it's legible, I don't mind. However, you know, it's going to make it harder every single time that you do this. And I have no limit to the number of times that you can turn an assignment in. Okay? So what that means is you could get an A in this class. Oh, what a concept. By doing the work to the best of your ability. So you'll see there's a limited number of summaries that we'll do throughout the semester. Currently, we have a summary of the Magtalioti paper. We have a summary of the methane paper. We have a summary of the plume paper. I'm about to give you another one. Really, Mateo? So every week we're going to get a new summary because we're going to practice reading, summarizing, annotating, etc. So we get good at it. And then you're going to kind of go off on your own direction. And we're going to start writing specifically for your project, something that you're interested in. Right? Then you'll be reading papers that you like and summarizing them. Right? Okay. That means that in the writing intensive course, you will be writing intensively. Okay. So even though we only meet once a week, how much time are you spending outside of class on this? Yeah. A lot of hours. So if you look at the number of units you're getting for this class, right? One unit is, I think, 3 hours per week. And this is something like a 4 or 3 unit class. You're supposed to be spending somewhere between 9 and 12 hours per week. Does that make sense? So even though you don't see me, doesn't mean that I'm not there. There's a lot of ways in which we need to be interacting. So many of you sent me the requirement for today. In addition to writing up your summary, you sent me the paper. Raise your hand if you sent the paper. Raise your hand high. Okay. So some of you didn't. Okay. The longer that we take to do any of this, the more we're going to fall behind, the less you're going to be able to do, the less well you'll do. What week is this? Yeah, so let's have a look here. What did I write? Okay. Whoops, wrong class. Just kidding. Okay, so this is week 4. So we're going to start doing check-ins very soon. What's that? These will be one-on-one meetings. So as it mentions in the ungrading policy on the syllabus, linked in the syllabus, you are going to be graded on your performance overall, and we will have 2 check-ins and a final check-in, right? In your Phys 4400 class, that may or may not include doing problems. In this class, it may or may not include whatever sort of synthesis of the class is necessary. I won't have you be writing in person. That would be extremely stressful. Okay. But that means that I'm really going to be checking in with you because we don't have that much time. We have 3 5-week breaks, essentially, like blocks in which we do all of this work. And we're almost done with the first one. Okay. And if you only came to class and that's it, that means that you've put in 4 hours of the class. Right? That just simply won't fly. Yeah. You have a question? No. Okay. Just sometimes. Okay. All right. Any questions so far? Okay. So I'll ask you to sign up for check-in sometime next week. Okay? Send me an email, arrange it personally. Shouldn't take longer than 30 minutes. If you're in both of my classes, block an hour. I don't want to. Yeah, you might as well. I mean, if you don't want to, you can do them separately, but you just have to coordinate your schedule with me. Well, one for 30 minutes and the other for 30 minutes. Because you're in 2 classes with me. It will take an hour. No, just kidding. Maybe it'll take an hour. Well, all of it, everything you're learning, right? It's the same way we did it for fluids. Everyone remembers it for fluids? Who was in fluids? No, you just blanked that right out. Okay, well, we'll make some adjustments. Okay, so for the science part of today, you are going to be taking a new paper This is by Kevin Zonley. He's awesome. When you hear him give a talk, which you may never get the opportunity to do because he decided to go into physics and not astronomy, because he don't like people with astronomy. He is just very fun. Because he doesn't take it. And as you read in this paper, the name of the title is there methane on Mars? Question. Yeah, so he's directly addressing a history that you wrote about in the methane paper. So there's many other papers, and he said, is this reasonable? Now, the middle section of this paper is completely untenable for you. Do not attempt to jump into it unless you love spectroscopy. Okay? Remember how we read papers. There's no... Oh, sorry, Kobe. There's extras right there. Okay, wait. 2, 4, 6, 8, 10, 11. Who are we missing? I don't know. Someone's missing. John. Yeah, I'll take it back. Okay, actually, I'll use it right now. So how do we read papers? What's the steps to reading a paper? Read the abstract. Good. This one, the abstract is straightforward. This abstract is fine. It's one paragraph. It's a little technical, but it's not horrible. Okay, and then we're gonna. The title comes with the abstract. What? Images, yeah. So we'll go to the figures, and we'll notice there's no figures on the first 2 pages. And then there's some figures here. Ooh, these are tricky looking figures. Okay. This is a paper about spectroscopy. No. This is very complicated spectroscopy. I do not expect you to read through these figures and understand. What I would like you to do. Why is it so fast? Yeah, because he's trying to debunk a pretty contentious topic, right? And you're basically going to be looking at the introduction where he describes the controversy in the way that he sees it. And then some of the summary associated with his viewpoint, the discussion and summary here at the bottom. And I want you to summarize those pieces. So whereas before we annotated the whole paper, but it was generally written for a very broad audience, this is not a review article. This is not a Nature or Science paper. And so those are generally easier to read. That's why we're starting with your own review paper. This one here, you'll notice, where does it say it? Is an article. Sometimes they'll say letter. Letters are shorter than articles, but they're more specific, right? So this is incredibly specific. You're welcome to read the whole thing, but I'm not going to require you to do that.
Which parts?
Summarize abstract, introduction, and the introduction goes through to this section here, this section on variable methane as an extraordinary claim. And then in absence of extraordinary evidence, I mean, you're welcome to read through this first 1, 2, 3 paragraphs here. And then he just goes in, line after line after line after line on all of the spectral evidence. And I'll just tell you, it's tricky, right? So rather than going through and trying to understand all of the spectral data, you can go to the discussion and summary, right? And using what we talked about last time about determining credibility, talking about these claims of extraordinary evidence extraordinary claims requiring extraordinary evidence, right? He uses that specifically in here. That's one line, says extraordinary claim requires extraordinary evidence. And he claims that they do not show it, right? So you will then get to verify or look at his claim and say, I believe it or I don't, right? Think there's life on Mars or I don't. Make sense? Do folks have a topic picked out? They just haven't sent me the paper? No? Yes? Yes? No. Okay. Okay, I wrote this slide 2 years ago. It turns out to still be true. And I'm not speaking to one person in particular, but I am just keeping this in mind for how long the semester is. The semester is 15 weeks long, right? And we meet once a week. So this is just trying to hammer home the point that I don't get a lot of face-to-face contact with you for this one without your coming in to see me, your sending me emails, right? There is a huge section of this class, which is supervision. So, you know, if you don't do anything in those time periods, that extra time period, then I can't interact with you. Okay. Here's a textbook. It's this one. I show people. Someone has mine. No, okay, I lost it somewhere. So I stole this from Laura or Dr. Woodney. If you're going to do the astro part or an observation, you'll want to read this. You probably still want to read this anyway for the data analysis section. You are not going to read every single chapter. Most of this is straightforward, but we will talk about, you know, one of the most important scientific contributions that astronomy has made in the past 100 years, right? Computers would be maybe first, I don't know. Okay, and these slides are going to become less and less important. Mostly because I'll do a lot of the stuff on the board, and these will be sort of notes afterwards. But, you know, like I'm doing right now, just talking, that's where you're going to get your information. So if you're relying simply on the slides, that will suck because you'll need to keep notes. Okay, but thankfully everything's recorded, so you can replay the recording. Did anyone not know there was recordings? Okay, yeah, sorry, I forgot to mention at the beginning. So there is a YouTube channel that I try to upload everything to because I broke Canvas last semester because the files got too large. They said stop uploading things to Canvas. So, okay. So I said that we're going to talk about the introduction. We're going to talk about chapter 2, manufacturing, some CCD gain, and dynamic range. Before we do that, we need to talk about how telescopes work. People familiar with how telescopes work? How do eyes work? There we go. All right. Here's your eyeball. Okay. It's pretty good, right?
That's good.
That's pretty good. For first try, that's a great eyeball. Okay. So what's this here? Lens. And how does it take light? From all of this side, right? Light comes in from this side and it focuses on this side, right? And on this side, we have a nice curved surface. And yet I can see all of you in 3D. Oh, amazing. Huh. Okay, so let's take a little tree. Okay. Pretty good tree. 2 for 2. All right. What does that do? Goes through. Okay, so let's draw some lines. Now what? Goes down. Okay, so now it bends. Okay. Oh. Is this true?
Yes.
Yes. What happens afterwards? Your brain interprets the image and flips it over. Okay, so if we look through a telescope, what do we expect to have happen? Telescopes are built of what?
Oh.
I was doing so good.
Same thing.
Same thing? How many lenses? 4 lenses, 1 lens, 6 lenses? 2. You have 1 lens here. This is the primary.
Oh.
And this is the secondary or eyepiece. Is this how all telescopes in the world are constructed? No. Is this how any telescope at the observatory is constructed? Nope. Okay, so at the observatory, we have a different design. They're smaller. And they look like this. What's happening? What? Yeah, there's mirrors. Okay. So in fact, we can reduce the length of the telescope by using mirrors rather than lenses. What are the problems with having lenses? Well, glass in general is heavy. And if you think about the shape of this lens, like that, you have to hold on to the thinnest parts. Right? So imagine it. It's holding on to a big, thin piece of metal, and it's heaviest in the middle. And then you point it straight up. Where is it likely to fracture? Right on these very thin places. Okay, so let's avoid that construction, and let's use mirrors. So here, I'm now going to keep an open hole, and I'm going to put a curved mirror this way. So light coming in from infinity will collect here, be focused, right? And then maybe somewhere along here, I can put either a CCD, which we don't know what that is yet, or I can put something that will divert that light to an eyepiece. Okay, so this would be like a curved flat mirror like that. So sometimes you'll see a telescope like this pointed at the sky, and maybe they'll have them on the street, and the eyepiece is right near the front. Well, that's what's happening. Reflects off the bottom, bounces to the top, and then goes out to the side. And the eyepiece is like right here. Right? Sometimes they're down here. What the heck are they doing down there? It's lost, right? Sometimes they're in the back. What the heck? How'd the light get back there? All right, let's look at all three of these examples. Oh God, that's the worst that ever happened. All right. Okay. So this diagram makes sense. Okay. So we suspend something right here in the middle. And it's going to be a little flattened piece like that. And it's going to go to an eyepiece. Yeah. Okay. That's one way to do it. Okay. Or you could suspend something else here. A what? Another mirror. What would that do? Good. Yeah, of course. So let's add another mirror here. Now, where does that send the light? Send it back that way. And let's cut a hole through that. And let's focus this light through this hole. This is how all of the telescopes that you see at the observatory will work. Okay. They have these little bars to hold up the secondary mirror. They send it back here. If you have the ED scope, the littlest one, this is just the camera. Okay. The big ones, they have a hole. And you can see that they have this hole because you look at the 17-incher and there's a hole. Okay. Is there any problem that we have with the fact that there's like a half, little hole in the actual mirror? Does that affect the image quality? No. The trick half. Okay, so you may have done this problem when you were in optics in 2500, 2010, something like that, 2510. Okay, let's just imagine the same idea. Here's my very good tree. That's not a bad tree. Okay, here's your lens. Okay, let's cover up half of it. Can I still form an image? What? Only of the bottom part? So you're thinking about like covering your eye and then like it's actually blocking out stuff, but you're not actually covering up your lens. Your lens is very small. And you might have hair. A lot of people have hair in this room that covers their eye. And yet you see perfectly fine. Exactly. Light is shining in all directions. So you can get some of these here going back this way. Oh, snap, right? It's not just straight. And in fact, you may have shown this when you did optics. It's not a hard proof. But if you cover up more than half your eye, that's when you start not being able to make an image. You're not covering your eye when you do that. Right? If you do this, you covered your eye. But your lens is really small, right? Your pupil or your iris is really small. So to cover that up effectively, you have to use like a piece of paper too. Well, make sense? Okay. Even if you squint, you can almost make out an entire classroom. You notice that? Lenses are cool. They take in light from everywhere. Okay, so the same thing is happening here. And we don't care that we have this little hole in the lens because that cuts out a very small effective surface area. And the trade-off here is that, in fact, we have better maneuverability. So instead of telescopes being 30 feet long that they used to be, I recently went in Tucson. They have the telescope that they found Pluto with, and it's 25 feet long because they found it 100 years ago, 130 something years ago. So those are great, but it just takes a while to move. These are like work, right? Questions about how telescopes work? Yeah.
And like not there. Like that you erase, like how small would that actually feel?
That piece. We'll see it on the 17-inch. So on the 17-inch, right, that's almost 2 feet, like that. And the hole is like this.
No. What? When isn't like when light goes through a really small slit, you get like that like diffraction?
Yeah. So you have diffraction on the whole thing, right? Anytime you see a star, and it looks like that, what's happening? What? On the crossbars. So this is diffraction on the thing that is holding up the secondary mirror, right? For the EV scopes, there is no secondary mirror. That is where the EV scope is concentrating. But either way, you have crossbars necessary to hold up that piece. So when you look down the barrel of any telescope, you will see a cross. And that is the diffraction from the cross. It turns out that they optimize the rest of the optics so that you don't get a lot of diffraction in the center. But what you're thinking about is called an airy disk, where you have some circular diffraction pattern. And that's usually swamped by other sources of noise. Okay. Questions? Comments? Concerns? You will see stars with the telescope, and they will not be 1 pixel. Is that a problem? Yeah, they'll take up many pixels. So let's say I have a picture. Why is there so little chalk in every room that I go to? This is all I have. Is there chalk on that side? Okay. So let's say this is an image that I make. Okay. And in this image, there are stars and galaxies and everything else. And let's say here's the galaxy. Okay. And then here's some stars. Am I seeing the size of the star? No, I'm not. Okay, so let's have a different one. Here's Mars. Or like here's Jupiter in this part of the picture. Okay, and I can see features on the surface, right? So I can see like individual features on Jupiter, maybe on Mars, I see like a little red dot or something, right? That size is relative to the fact that the object is large or small and farther or close to us, right? So currently, this is much larger than, say, someone's face in the back. However, this has the same angular size as that object in front of Jose, right? To me. To you, it's much larger, right? That's a function of angular size. We talked about this when we talked about the width of your hand, your finger, etc. So my question is, here, you get individual pixels that make the image, right? And they represent real places on the body. Is that true for stars? It's just brightness, but why is it more than one pixel? It's diffraction, right? This is the diffraction you're talking about. Becomes circular, right? It's uniform, becomes brighter, but here, individual pixels, right? You can get closer. You can get closer in space where you don't have atmosphere, won't wiggle as much, but you have limitations just based on the fact that every star is really, really far away, right? And is very small in comparison to that distance. So they all should be a single pixel, and yet they're not, because of diffraction and because of the atmosphere. So this is sometimes why you go up and you try to take observations, and I say, the seeing is really bad. The seeing would be the wiggle from the sky. That's something that can get better or worse. The telescope optics, those are fixed. Bigger telescope, better. Huh? Why is that? Why bigger telescope better? What? Not only take in more light, so that helps you see darker, but how can I get a more precise image? What's that? Yeah. So the question I'm asking here, there is a relationship. Okay. We talked about airy diffraction. Okay. That is the diffraction of light in a circular pattern. Right? If I have a telescope and I make it larger, I'm telling you that the resolution of the telescope gets better. Why is that? Not necessarily its ability to see better at night. So my pupil dilates and contracts. That allows me to take in more light or take in less light. And yet my ability to resolve things, right, to read at a certain distance is fixed. If I cover one eye and I walk around all day, what am I going to do? I'm gonna bump into stuff, right? Why is that? Because my depth perception disappears, right? You have one eye, you have one less depth perception. Your eyes right now have two things, and they are able to distinguish better because they act like one giant eye. It's a very weird thing, but having multiple eyes gives you better diffraction capabilities far away. So you see, for example, I mean, I don't know if it'll be quite dark when we go home. As you drive home, don't go very fast while you're doing this. Maybe don't do this while you're driving, but stand like near a freeway and like close one eye and see how far away you can see two different lights on the car's front versus one. Not quite. So imagine, so like you have a car with two headlights, right? You can see the difference between them when they're close, and far away they look like one. Okay, that is your ability to resolve, to see the difference between two lights. So I ask you to cover your eye, right? And see how well you can resolve lights that are really far away compared to when they're both separated. The wider you can get the light from, right? Big telescopes have the ability to take light from here and from here, and therefore form a sharper image on the back, which can resolve where these things are coming from. Does that make sense? Okay. Hold on. Let me show you. Small lens, big lens. Okay. Object here, object here. Let's say they're putting off light in all directions. Okay. These wave fronts, as we think of light as both particles and waves, right? These ones here. Some of these are going to hit the edge out here, right? Just like we talked about with this other one, they can go around the edge. These ones, some of them, going to go way up here, right? And they're going to be focused in the back, right? If they add up, they will appear to be on top of each other. They constructively interfere, they'll be on top of each other. If they deconstructively interfere, they'll appear separated, right? We remember this, area diffraction? Okay. The size of the diffraction ring is dependent on the size of the lens. Okay, so if I put two telescopes, one here and one here, I can get an effective resolution as though I had the whole thing. This is how we can see the black hole at the center of our galaxy. Because we can create an effective telescope that's the size of the Earth by taking simultaneous observations from one half to the other. Now, you would need to cover up that entire space with mirror or lens in order to get that much light, but we don't want that. We only want to be able to resolve that well. Does that make sense? So the telescope does two different things at the same time. It takes in more light and it resolves it better than your eye does. That's the only argument I'm trying to make. Right now, you have two telescopes that help you take in a combined resolution of the Cyclops eye. Do you see? Yeah.
Does the area of observation become bigger if you're observing? Or
Our field of vision is, I mean, I think enhanced by the fact that our eyes can move.
I'm sorry.
For the telescope. No, telescope doesn't matter. Our field of vision, that is going to be a function of what it is that's doing the observing. So we'll talk about how CCDs of different shapes change the field of vision. Right? Because this is getting light from everywhere. Right? Until I put a little tube on it. And then that fixes it. Now it can only get light that's going in parallel. All the light that comes from a star is coming in mostly parallel, except for stuff that's in the way. We good on telescopes? Okay, things that we're going to look at home. I think it's spelled like this. Area diffraction. And that'll be in your night book, the 2500 book. I know, you never thought you would have to remember the 2500 series. Oh, it's right there. What's the name of that book?
Physics for scientists and engineers.
Yeah, but the author?
Yeah, Randall Knight.
Randall Knight. So if you open that book up, you'll see this picture. Okay? Yes or no? Okay. What is the most important discovery that astronomy has given us, you and I, day-to-day lives in the past 150 years? Feelings. That's not 150 years. Yeah. No, that's 6,000 years ago. Yeah. Oh, yeah. That's ancient people knew that shit a long time ago. 100 years ago. The question is, what type of technological advancement is the most important to you in your daily life given to us by astronomy in the past 150 years? Cameras. Why cameras? How cameras come from this type of technology? What? Save an image? So in the old days, right? You may have seen these before. You would take a picture with something called film. Okay. And you used to expose chemicals to light for like a fraction of a second, right? The shutter would go, right? And you'd expose those chemicals, and then you'd have to take it to Rite Aid, right? And you'd be like, here, sir, here's my chemicals. And then they would take those chemicals and they'd put them onto other piece of paper and they'd hand you back your pictures. Right? It was super cool. Anyone actually have non-digital cameras growing up? Okay. Yeah, like the disposables. And you get a little roll and you turn it in, it's film. Okay, cool. So that's how you would take film. Before that, you would have, for example, not everyone used to have cameras at home. You would have like little plates. So you've seen maybe the old Westerns, and they would put their head into like a little thing, and then they'd hit some big button and go, right? And then the piece of glass would like literally explode, right? So what's happening here? You're creating a bunch of light. It's bouncing off the object that you're trying to observe. And then you have some piece of metal with chemicals on it, expose it to that light, and then you close it back up again. And that's how you create your picture. Okay. So that's how we did it for many, many years, right? We found these chemicals that are light sensitive, and we said we can transfer them onto this thing, and then we can make multiple copies of it, right? Okay. And then you have quantum mechanics. Not quantum mechanics again. Oh, I hate quantum mechanics. Okay. And basically you develop something called the CCD, the charge coupled device. Okay. The charge coupled device allows us to take observations, collect photons during a certain amount of time, and then turn that into information. And that's the process we're going to talk about today. The very first section here, chapter 1, the introduction, shows you what a CCD is. People have this book? Physical book of it? No? No. You have it? Good. Okay. So you can see these CCDs. Okay. The face of them are mostly black, this greenish, blackish color. Okay. Let's see. For the most part, we'll be talking about CCDs, at least on Earth, that are exposed to visible light. That's the type of light that gets around well in our atmosphere. But you may have seen infrared cameras. Almost all cameras today use a form of CCD, first couple device. And we're not going to talk about exactly what they are. But essentially the picture, the one that I like, is essentially something like this. Okay. So imagine you have a field that's sitting out somewhere in the desert or something, maybe football field, and you put a bunch of buckets, literal buckets. You stand them all right next to each other. Okay, so this is a bucket, and this is a bucket, and this is a bucket, right? They have a finite width, and they can collect rain. Okay, and then you wait for it to rain, and all the buckets collect water. And maybe it only rains for a little while, but all your buckets are outside. And you go and you look and you count, you use a ruler and you count at the bottom of the bucket how much water fell in. And you measure no water in this one, 1 inch in this one, 2 inches in this one, 1 inch in this one, no water in this one. Okay. This is what your CCD is doing. Except instead of collecting water, it collects photons. And the photons, okay, basically, we'll talk about this, are going to cross a metal substrate. What? No. Photons get absorbed here at the top. They force electrons to jump. The electrons will fill up a little well with charge. And then we read out how much charge is in there. Okay, so here's the physical example, the one that we can kind of understand. Here's the quantum mechanical example. This can be a lot harder to understand. Okay, this piece here takes rain in, and you go in and you measure every bucket. Okay, this process makes sense? Quantum mechanically, photons come in. They force electrons to jump into a bucket in a process that I'm not going to describe to you yet. Okay. And then you read out the charge down here. Okay. Make sense? That's what the camera does, yeah. So your eye does. Your eye is also doing this, but your eye is not as fun. It's a lot harder to do. Your eye is like the best camera in this room because it has a huge dynamic range and it has this like interpolating processing that like your iPhone could never. Right? Biology is much better than technology just because it had like 100 million more years to evolve. Right? Okay. What are the things that I want to point out? So we've talked about the types of CCDs. Most of them are something like 512 by 1024 or 1024 by 1024. I don't even know why we use these numbers, number of pixels. So like, it's not like 10 by 10. If you look at a CCD, right? Any standard CCD size is not like 1,000 by 1,000. This is pixels. Not bytes, but it does have something to do with what a byte is. Zeros and ones or a binary, right? So here, this is not exponential of 2. So 512, 256, 128, 64, 32, 15. So you see the powers of 2 going up to 1024. Okay. Because it's something squared. Because it's a square detecting the depth. So usually you don't, when you manufacture CCDs, you don't go like 10 in this direction and 14 in that direction. You do 1024 by 1024. Okay. Another question we have. This one's fun. Have you seen this one online already? Here's your phone. Okay. The lens is what shape? Circle. But the picture? Oh, how? People legitimately ask this on podcasts, and I always write in there. Why? What? Did you say magic? So the reason why the image is rectangular is because of this picture here. These are the CCDs. The CCD is a rectangle. The CCD is a rectangle because the screen is a rectangle. If we wanted to, if we were really crazy and maybe didn't have like rectangular looking hands, if we had more like octopus hands, maybe we'd all have circular phones. And the CCDs would be circular. But guess what? Those are pretty hard to manufacture. So manufacturing CCDs is much easier because they're in a line. You just set out row, 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 and then you connect them with wires. Okay? Yeah.
Why do all cameras look circular?
Why do all cameras look circular?
Yeah.
Well, the lenses are easy to manufacture circularly. Because then they're orientable, right? They take in light from all directions. What happened? Hello? Did my PowerPoint just fail? Oh, it's updating. Of course it is. Okay. Did that answer your question? Did that answer your question or no?
Just because they can rotate, that's why.
Well, think about a lens that is not circular. The lens being non-circular would look like what? A different shape. Would it be able to focus in the same way? No. If I cut, say, a lens into a rectangle that curves only this way, does it create a perfect image or does it distort you like a funhouse mirror? Okay. All right. So we have to talk about something called quantum efficiency. You might have seen, so this is the picture, by the way, that I tried to draw. Not very good. But in practice, this is the idea of what happens inside of a CCD. And so you can read more about these as we go through. Oh my God, this thing won't stop failing. Okay. That's okay. It's not that big a deal. So in practice, I'm not going to yet talk to you about how the substrates work or anything like that. I think that'll definitely put you to sleep. But we'll talk about what we need to do in general. So we have a theoretical process, okay? And the reason that I said that it takes quantum mechanics is because before quantum mechanics, we as human beings did not understand the idea that light and matter could interact with one another in specific ways. And what I mean by that is this light creating an electron jump is due to something called the, you know this one? The Zioelectric effect, right? You take a photon in, right? You can get an electron to jump. Okay, it doesn't matter. We needed to characterize this. So certain metals do it and certain ones don't, right? So you can use electricity to make light, or you can use light to make electricity, right? That's a relationship that quantum mechanics give you. The early 1900s, you've seen this before, right? Maybe you've seen, maybe you have like a gas stove, right? And you hear this, and then it lights the flame, right? So you apply electricity and it makes a little spark, right? Those are piezoelectrics, right? Okay, so in this particular circumstance, we had to understand this process to understand how you could take materials that were good at giving up their electrons when they encountered light. So essentially, you have to find certain types of light, or sorry, certain types of material that like to give up their electrons. We will know what those certain types of materials are. Yeah, what type of metal? Okay, specifically. Yeah, that's certainly one of them. What's that? Silver. What's the easiest? Why does this keep doing this? I'm not doing that, right? Okay. It's the name of a certain place in California. Silicon. Silicon is the most famous one. Silicon, like silicon dioxide. So if you silicon dioxide, you have some things here, right? We found out that silicon is really good at letting it have other friends have its electrons. Okay. And this is how you can send messages. This is how you can encode material here. Okay. And then you can measure potentials. Okay. So in fact, I can show you what a CCD looks like. This is your figure 2.4. But well, maybe I won't talk too much about the piece here. But essentially, this is what it looks like. You're going to have some junction. Well, it's the same picture. I'm not going to draw the picture twice. You have some junction here that lets light in, and then it will deposit electrons due to the conversion of that light. And then you simply move the readout area underneath. So what that means is that you have some field, right? Here. And as you walk through each piece of the field, you're just measuring how deep the water is. The computer does the same thing. You have some CCD. It's going to step over every location and determine how much charge is in that location. So that can happen in a number of different ways. You'll have wires that are either connected on the edge of the CCD here that read out in order, or every single CCD has a wire coming out of it, right? The pixel itself has a wire. Does that make sense? Yes or no? Okay. Let's see. You'll see some examples of here, different CCD types, back and front illuminated. Generally speaking, you'll have some examples here where we talk about the we'll talk about the ability or inability for a CCD to see at all times. So if you point your phone at the sun, what happens? It gets really bright, right? And here you have an example in your book of what happens when a pixel gets saturated. So that means that the bucket becomes full of water. Okay. So what happens when the bucket becomes full of water or the bucket becomes full of charge? It spills. That's exactly right. So this would spill into here. And would this be a reliable observation? No. And in fact, when you look at the book here, you'll see what happens in two different types of readouts. So here, this type of readout, you read in columns. And so if you have a fuck up on this one, all of them get fucked up. Okay. Whereas here, this one's a little bit better. It's still bleeding into the ones next to it, but the way that it's being read out saves you a little bit. This is more of a technological difference, but understanding saturation is really important here. Okay. If we look at something for too long, okay, we're going to get a flat. It's going to be whatever it is. So mostly when we think about like a star, there's a point here. And the way this is going to be represented on our telescope is like this. Okay. So this will be brightness. Okay. And if I take a cross-sectional area like that, across the pixels, it'll have a central peak, a dot, right, on top. And then it'll kind of go off because of diffraction. If it was perfect, it would just be a delta, right? Just that one pixel that gets light. But because light leaks out through various different techniques, you get all of these pixels nearby having the light in it. But if this bin in the center here fills up and starts spilling into nearby bins, what do you get instead? Here's the pixel in the middle. Here's the star. What? It looks bigger. Yeah, it looks flat. Right? Do stars have a cap to them? No. But this is what we end up seeing in a picture. Right? We see some circle, right? Rotate in your mind this 360 degrees and then look from above. That's going to look like a circle. Right? The process makes sense? Okay. I'm throwing a lot of CCD stuff at you all at the same time and expecting none of it to stick. But we're going to say these ideas over and over. And in particular, we're going to grab this book because understanding how our technology works will be essential to understanding its limitations. Okay. In particular, yeah.
What makes the pin bigger?
This is a manufacturer choice. So we buy a certain number of pixels. Now, that certain number of pixels may represent a smaller or larger area in space, right? So very early CCDs, 1024 by 1024, right? You can get a pretty good image with 1024 by 1024, right? As long as maybe you map over the area, okay? You get a nice picture. 4K resolution would be 4 times that on a side. And of course, it's a multiple of 1024 times 4, so something like that. Okay. Super high resolution cameras will give you that, the digital type of camera. But another thing that we haven't even talked about is how this fits into the optics part. So depending on what the focal length of the telescope is, that will help you determine how wide on the sky you are viewing versus how many pixels you're putting on a small area, right? If you have a small CCD, big telescope, small CCD is giving you a lot of pixels on the sky or a few pixels on the sky. Few, correct. And if you have a big CCD, lots of pixels, giving you a lot of sky area. Okay, so big physical CCD. But now, let's say I have on the big CCD a lot of individual pixels. Okay, hold on. Let me explain the concept twice. Okay, you have a field. Okay, on the field, you have two choices. Let's say it's a football field. Okay, here's a football field. You have a couple choices here. You can cover the entire field with collecting area, buckets of different sizes. So you could put lots of little buckets like this. Or you could put a few big buckets. You see the question? CCDs will make this choice. You'll either manufacture physically large CCDs, right, with large buckets, or small buckets. These are the physical sizes of the CCD. And they're relevant, right? Because they're physically taking in light. These are the objects that are like actual buckets taking in light that you'll have to measure afterwards, right? So there's two constructional choices. And then, of course, where you place it with respect to the optics, right? Okay, so how big a pixel will represent some fractional size on the sky, depending on these choices. Okay. Okay, I'm gonna stop here because that's a lot. Let's talk about where we're going from. Why did this thing still die? I'm gonna kill this computer. Well, you can see it up here. This is where we are right now. We're talking just very briefly about charge coupled devices. Those chapters that I put up to you, start reading them, right? Don't memorize the name of manufacturers. That's silly. Okay. Don't go in and try to understand every single piece of this book. But the sections that I point out will be important because the next time that we talk, we'll be doing data reduction. How do we go from your observation to understanding how to reduce it? And what I mean by that is, how do we go from light into a value? What's that actual process? Oh, I deleted it. You know, there's a picture. Light comes down, produce number. How number? Right? That's the next question. Okay. And in that question, we will find some fundamental questions about how well do we know the number that we got? So if, for example, and this is the piece that I'm going to let you think about when you go home. Let's say for some reason you're like me and you, when you're bored and you're going to check out at the grocery store, you always measure how many people are in front of you. Okay. It's a weird thing, but you do it. Okay. If you did it once, how many people, let's just give me a number, how many people in front of us? 4. Okay. And then you do it again, 2. And then you do it again, 10. And then you do it again, 3. And then you do it again, 7. That's a lot of people in front of you. You should pick a different line. So, okay, so here's this idea. You're going to get all these numbers. No one said the same number twice. That's weird. No one wanted to do 2 again. No one did 0. There's limited choices of how many people can be in front of you. Similarly, photons, light from a distant object, comes in limited quantity, multiples of a real number. Okay? How certain are we that we got that many photons from somewhere? Well, there's a formula. Okay? We'll understand that phenomenon. That'll be the data analysis section. Okay? How confident are we that we actually got the answer that we claimed to get? That's something that we'll figure out in this class. Okay? The process makes sense? Okay. We understand what the reading is? What we're supposed to be doing? Okay. You know that next week you're going to we're going to talk about abstract design. Okay. We are setting up essentially to do a proposal. Okay, we're headed towards there. We're going to not actually do the research in the proposal, but we are going to create an abstract, an introduction that summarizes the field to the best of our knowledge, and then proposes to investigate XYZ. Okay. And we'll learn how to analyze one another's writing.
Next week, we look at submit this summary for the previous year, or the one we got last week.
So you're always about 2 weeks behind. What I mean by that is last week, you gave me this one, the Metagliotti paper. Today, you gave me the one that you got 2 weeks ago. Then you'll give me, sorry, on this week, you'll give me the one, not the one that you just got, but the one that you got last week. Right, so you're always about 2 weeks behind. So you should have about 2 weeks to annotate it and write the summary. Annotate, write the summary. Right? Is that correct? I'm not wrong on this timeline. Yeah.
The methane 2 days ago. I submitted it last week. And now last week they got the letter. I submitted it today. Or I submitted it next week.
No. So the letter that you just got, you'll turn it. Oh wait. That one.
This is it today.
Let's do next week. Yes. Right? I think that's right. Yeah. Because I just read Metagliotti, right? And I just gave that back to you. And then I'm just taking now either methane or the plume, right? And you have already read both of them, but you've only summarized one of them to give to me. Yeah.
And then
Yeah, I mean, I'm gonna stamp these when I that's why I brought this thing. I don't know what you're talking about. Uh-huh. No, I think they're supposed to turn it in today. Oh, okay. Yeah. I want you to annotate. I might have stamped your annotation. No?
so you can stop.
Oh, but didn't you want to keep working on it because you guys wrote the same one? Yeah, so that might be what happened.
And then for the review paper that we had 3 weeks ago, that we had sent you, can we just read that one, and then what?
That we haven't talked about that yet, right? So that'll be the start of where we're headed. So right now we're doing what is essentially I call journal club. Right? So that's the process of getting together. We're all reading a paper and then we're gonna kind of talk about one another's summaries. So after you hand me in the plume, like this one here, we're gonna do some peer review. We're gonna read each other's work. Oh no, I hate that. Right?
So when should we start reading the one that we sent with the review?
You can read that whenever you want. That won't be due yet. We'll talk about when that's due later. Okay, because you are going to be writing a proposal on your own terms, right? You don't know how to write a proposal yet. So you're going to be reading multiple papers. Eventually, you'll run out of papers that I give you, and you'll have to be creating your own papers week by week, right? And then you won't be turning out as many summaries. Okay. People feel lost still with what's needed for this class? Okay. There's a lot of writing.
So just to be clear, next week, we are bringing you a summary for Bloom and annotating the one that you gave us today.
Yes, but I usually say this in a different way. You start annotating right away and you're summarizing right as you go. right? It's just due later. Okay. Yeah. Oh yeah, let's pull this thing up. If it ever stops him failing on me. So this is obviously the wrong date. Don't look at the date. Okay. So I wrote when I wrote these slides 2 years ago, I said astronomical, planetary, helio, or earth science topic. If you want to do something outside of that, that's perfectly fine. You just have to contact me. I had some people already reach out with great ideas. Do remember a few things when you're looking for these review papers. One, they are review papers. Okay, this is the easiest way to enter any field. So don't read a letter, right? The letters are tricky. They're very specific. Articles are specific. They're highly technical. Start with a review paper. And then once you're comfortable with the field, then you can kind of get more specialized. If you're already doing research on it, great. No, I don't mind. If you already have some technicality in it. Okay. What I wrote. I was fast for the last 2 years. I'll edit this. This is 2 weeks. That was that up?
Yeah, it was Sunday.
Okay, so that's not true. I mean, this date's wrong too, right? It's not February. That was a long time if it's February. Okay. Well, spend the rest of the time that you need in order to figure out what you're doing, right? I don't want you to just finish class and then be like, done, and I'm not thinking about it for a week. No, I'm not stamping annotations anymore. All right, fine. I can stamp anything, yeah. Yeah. I don't know if I said that. I said I'll think about it.
No, you said you give a stamp on Thursday. You definitely said I'll stamp it on Thursday.
Oh my god.
I have it recorded.
I have it recorded. All right. Let's see. Do you want to stamp?
Yes.
Anyone still have stuff they want to give me? This is brown new what?
What were you stamping down?
Oh, just the ground.
Oh.
Oh no, not you.
Come on.
No, I don't have.
No.
You want to stamp on that too?
All this flat bottom.
Yes. Okay, so that was the 2018 article, right? Which means that as a review article, if you're looking for something that's in the past 5 years, in some cases, you're going to be able to summarize it well. That's great, especially if there's lots of a lot of citations, 30, 50 citations, that's great. But if you go back 15 years, right, that'll show you the state of the art 15 years ago. And usually that's a little bit easier to understand because they knew less things. Sometimes you'll look at a review article and it'll be on the very specific type of field that something has merged into, right? Superconductors under high stress manifolds. You're like, well, what the fuck is a superconductor, right? So maybe you want to sort of focus in first on some broad area. You say, oh, I like this. And recent reviews are going to be highly technical. That doesn't mean that you can't use them. It just means be careful that what you're looking at, even though it says review article, is not too specific, right? Detecting exoplanets 20 years ago, review, great. You know, detecting life on exoplanet atmospheres, pretty specific, right? Okay.